Calculus Day 3 Notes, Part 2. So now we're going to continue to analytically find limits of functions at undefined values. So what happens if we try to evaluate the limits below by the direct substitution method that was used in the previous 6 examples? Well, you look, the function is the same. X squared plus 4x plus 3 all over x squared plus 2x minus 3. Well, and when I substitute in negative 3 using direct substitution, okay, we're going to get 9 minus 12 plus 3 is going to be 0. And then 9 minus 6 minus 3 over 0. 0 over 0 is undefined. And then when I take the limit as x approaches 1 from the left and x approaches 1 from the right, doesn't matter either way, do direct substitution, I get 1 squared is 1 plus 4 plus 3 is 8, but then 1 plus 2 minus 3 is 0. So 8 over 0 is undefined. So what are we going to do? So we know we can't use direct substitution right now. So what we're finding out, just because a function is undefined at a value of x does not mean that a conclusion cannot be reached about the limit. Consider the rational function to the right from the graph of the function pictured, or excuse me, the rational function we were talking about right above, looking at the graph to the right, what is the value of each limit below? So the limit of this function as x approaches negative 3, well, the limit exists when the limit from the left is the same as the limit to the right, and they tell me where that hole is. So this limit is equal to 1/2. Now let's check the one-sided limit. So let's do as x approaches 1 from the left. Well, there's my vertical asymptote, but when I come from the left, it's going to be approaching there. So it's going to be negative infinity. And a one-sided limit, that's okay. And now for the limit as x approaches 1 from the right, again, that's going to be positive infinity. Okay, the task now is to determine how to find these limits analytically. How was it that we found the discontinuities of a rational function in pre-calculus? All right, well, the first thing we did is we factored the numerator and denominator. If a factor canceled, then the function had a point discontinuity when the factor was 0, because that was gone. But, and again, in the original function, it couldn't exist. That's where the holes occur. And then if a factor did not cancel from the denominator, then the function had a non-removable infinite discontinuity, which we know as a vertical asymptote. Okay, let me write those down for you. Okay, so those are what we discussed. Okay, we will perform the same algebraic analysis to find the limit of the removable point discontinuities. So let's do the cancellation process below. So the first thing I do is factor the numerator and denominator. I notice x plus 3 cancels out. And now, and again, when I cancel out, that's supposed to be as x approaches negative 3. What I canceled out was the factor x plus 3, which is when x equals negative 3. So I'm going to be able to find out what this limit is, because that's the hole that I took out, and that's where I'm evaluating this at. So now I just do direct substitution. Again, I said it's supposed to be negative 3. Negative 3 plus 1 all over negative 3 minus 1. Negative 2 over negative 4, which they gave us from the diagram up above, was 1/2. So that's how I can algebraically find the limit even though it's undefined. So I use the cancellation process. So I have to cancel first, then use direct substitution. That's going to be it for part 2 of the notes.